This presentation is an overview of toxin detection using microfluidics, presented by Michael Chan
and Chris Hoff.
Why microfluidics? First of all, portability. We can build microfluidic devices that fit in the palm of your hand, and because of the small size, we can use low amounts of sample and reagents, which lead to low waste and reduced cost. Also, microfluidic devices can perform rapid analysis of samples. How are microfluidics being used? We need to prep our sample before analysis. One way is through membrane filtration, which is a physical filtration to separate both insolubles and solubles. Microchip electrophoresis, which separates ions. Microchip electrochromatography, which separates both ions and non-charged particles. And micro-CEC, which combines both electrophoresis and chromatography. Microfluidics can be used for both liquid and gas mixing. The figure on the left-hand side shows two solutions mixing in the blue and yellow region. This is known as an alligator teeth design. The figure on the right shows gas mixing, where gas comes in and is absorbed into a liquid to be detected later. This can be used for atmospheric testing. After prepping and mixing the sample, we need to be able to detect toxins within the sample. Two primary methods we do that is through optical and electrochemical means. Optical is broken down into laser-induced fluorescence, absorbance, chemiluminescence, surface-enhanced Raman spectroscopy, while electrochemical is broken into amperometry, conductivity, and potentiometry. The figure on the bottom right shows a Z-cell design to optimize the path length for optical systems.
One method of electrochemical detection is the use of conductivity. The system uses two microwires within the detection bubble. This method is particularly useful in detection of toxins that can form ions. Electrochemical detection methods are useful for detecting analytes that are not optically active. In this system, chlorate was tested in drinking water with detection rates down to 5.6 parts per billion. Devices can also be coupled with another detector called a mass spectrometer. In the upper right, you can see the ionization nozzle is incorporated directly into the device. The lower figure shows how plumbing can be used if the mass spectrometer has its own ionization source. In using a mass spectrometer lowers the portability, but increases the sensitivity and variety of toxins that can be detected. This table shows the vast amount of work that is being currently done in the field of toxin detections with microfluidic devices. This includes a wide range of different detection devices and then also of different pollutants such as pharmaceutical drugs, bacteria, different metals, and inorganic ions. You can also see that the sample matrix can vary between drinking water, aerosols, urban air samples, and soil extracts. Many of the advances for toxin detection improve on many of the current limitations. Devices that are currently being developed will be more operator-friendly and allow real-time analysis in the field, also increasing the number of toxins that a single device can detect. Great advances have been made with the goal of having a fully integrated system, whereas sampling, sample prep, and detection is all done on a single device. Finally, having a device that extends past its one use. The device featured on the right is a paper-based device for detecting iron-3 in the environment and incorporates an electrochemical detection and also has a colorimetric section that allows instant feedback to the operator. And finally, here are our citations, and thank you for watching the video.